Okay, as the title says, in this video we're going to be looking at the buckling of columns. And for what we mean by buckling, let's take a look at what would happen if I were to compress or put a yardstick in compression. Okay, so here's what we're looking at. There's our yardstick in compression, meaning I'm pushing on both ends with a force P, and I want to know what force P would cause failure for this yardstick. This yardstick has a cross section of 1.4 inches by a quarter inch. And what we know to this point is if we have something in compression, we've already talked about that equation, our stress, sigma, is equal to P over A. Well, we have an allowable stress for wood of 5 ksi, meaning if we go above 5 ksi, we would have failure. So if I have this 5 ksi, I'm solving for P. Cross-sectional area is 1.4 by 0.25 inches. Solve for P, and what I end up with is that a force P of, what did I get here? 1,750 pounds is required for failure. Of course, this is not realistic. If you've ever taken a yardstick and pushed on it, it'll fail in much, much less than that. So, what happens before this load? We end up with this concept called buckling. And you've probably seen this before. What happens during the buckling process is it starts to bow out. So you can imagine if I'm just going to draw this in like a stick diagram, and if I were pinned on both sides, which if I were just holding it with my hand, it'd probably be like that. I can imagine as I start to put force on it, it bows out and around like that. And we reach this point where once it starts to bow, we have this off-centric loading, right? So the more I push, the more it bows, and we call that an instability, and it creates failure. So in order to come up with the force that would cause that, there is a longer equation that we could develop using Diffie-Q, but instead I'm just going to give it to you in the hopes of keeping this video somewhat reasonable in length. And that buckling equation looks like this. Our critical force that would cause failure is equal to E, which is our modulus elasticity, times I, moment of inertia of the cross section, times pi squared over, in the denominator we're going to have KL squared. Um, so once again, PCR is that critical load, and L is the length. Now I don't have it actually labeled on here, but it would be the length of our column. E is our modulus elasticity. I is our moment of inertia. And K. So K is the new variable we haven't seen before, and K is going to be called our effective length factor. And we have this thing called an effective length. You won't hear me use that term as much. An effective length is equal to our effective length factor times the length. So in essence, what it is it's a way to manipulate this equation so that we can vary our connections on the ends. Meaning this is a pinned connection, and because of that, I get this parabolic looking shape, right, as it starts to buckle. Um, but what if it is not pinned? And if it's not pinned, we can talk about what the length looks like. So let me draw out all our possible scenarios. The first one being, so we can compare it, this pinned case. So with a pinned case, this is our general shape, the one I just drew a second ago. With that shape, our K value is going to be equal to 1. But what would happen if we were to fix one end, or actually fix both? Let's start with that. What would we call that? A fixed. And with this fixed column, you can imagine rigid supports on both top and bottom. Well, as it starts to bow, in this case, it can't rotate at the two ends, so I end up with a shape that looks a little bit like that. And because of that, I can see that my overall length, if we called this length right here, and I wanted to model this length, well, it's really just like that much of it, right, to get the same shape. So that's our effective length. That's what we want to do in order to come up with this variable k. And in this case, anytime you have a fixed column, you're just going to use k of 0.5. It says, and you can almost see how it would be half of the total shape. And then we could also have halfway in between, or fixed pinned case. And in that case, we have one side is fixed, the other side is pinned. Doesn't matter which is which. And you can imagine, since one side can rotate and the other side can't, then I have the pin up top, so it comes down and it has to come back in. And we get a effective length that's somewhere in between 1 and 0.5. And in fact, what we're going to use is k of 0.7. Now, the only other option, or only other scenario we need to look at, is what if we have a fixed on one end and free on the other, meaning there's no support on the other side. Now, as I apply my load straight down, maybe you can imagine what this thing would look like, and I would end up with something that looks like this. Right. Well, how do I map out what the overall effective length looks like for this case? Well, the effective length would include if we carried it down the other direction, right? So it's to get much bigger, so our k value is going to be greater than 1. And in fact, this is like half of the curve, so our k is going to be 2 to give an overall effective length of twice the height. So in essence, what you're doing with this is you're using this buckling equation and you're just subbing in the correct k value based on if it's pin, fixed pin, or fixed free. I didn't really draw it in, but each one of these, of course, has a load on it. It's your P critical that's pushing down, causing the instability. All right, so let's go back to this example we started with then and re-examine what force would cause the failure of the yardstick. Now, the key to this is the moment of inertia. And we're going to say it's pinned in this case, so we know our k value is going to be equal to 1. We said earlier our cross-section looks like this, where we're a 1/4 inch, 0.25 inches on the base or on that lower side, and 1.4 inches on the other side. And the reason I was careful, I just changed that and I didn't say, well, maybe I shouldn't say base, is because technically we have 2 moments of inertia for this cross-section. Because remember, the moment of inertia is 1/12 bh cubed. But that base is all relative to which direction we're talking about. Like, who says we can't just turn our meter stick 90 degrees sideways, right? So in this case, I do have 2 moments of inertia. One would be 1/12. The base would be that 0.25. And the height would be 1.4 cubed, giving me 0.057 inches to the fourth. The second one would be 1/12 times 1.4 times 0.25 cubed. Gives me like 0.00182 inches to the fourth. So which one are you going to use? And here's the key here. If I look up the equation and say which one would govern, well, it's going to buckle in the direction that has the lower P critical, right? So the smaller I value will govern. And what that means is that the base is the direction of buckling. And you can maybe envision this, that if I'm looking up at a plan view, bird's eye view, looking down, and I'm pushing straight down on this cross section, it's going to buckle to the left or the right, not up or down. So if you have a meter stick or a yardstick, try it out, or even a ruler, but it'll always buckle in that longer base direction. It's stronger in the other direction, right? So when you talk about this moment of inertia, your base will be that longer side, as long as the connections are the same. Pin, fixed, all that kind of business. So let's go back to that example then and finally plug in the numbers and find out what load would cause the buckling. We have EI pi squared over KL squared. So once again, we have K is equal to 1. I have the length of 36. This is 36 inches, 3 feet. And just plugging that E and I value, squaring that denominator, I ended up with 27.8 pounds, which sounds much more realistic if you've ever tried to break a yardstick. It's not that difficult. You can push with 30 pounds. You could break it. It would buckle. All right, but that's an overly simplistic example. Let's take a look at something more realistic. All right, so here's our example. What we have is we have a bracketed column. These brackets are at A and at B, and let me erase this for right now. And it's a 2 meter long length to this column. Um, and this is the way these brackets oftentimes will work. You can imagine there's a pin right here at A and at B. Well, that pin allows it to rotate, meaning it can buckle out this direction as if it is pinned. However, if I look at those brackets, and if it were to buckle towards me out of the page or into the page, it would act like a fixed because these brackets don't allow side to side rotation. They only allow rotation in the one direction. So you've probably seen these brackets before. Pretty common. So let's see. And I'm given that the X direction buckling is pin, and that's that left to right. Y direction buckling is fix. That's towards me, away from me. E value is 200 gigapascals, sigma y 360 megapascals. We want to find the maximum load before buckling, which is P critical. There's our cross section right below. It's a 20 millimeter by 30 millimeter cross section. So the issue here is we actually have to check both scenarios. Will it buckle towards me or away from me, or will it buckle in that left and right direction, in the X direction or in the Y direction as we look at that bird's eye view? And each one of those, the key to these problems is trying to get the right moment of inertia with the correct connections so that we can figure out the K value or the correct K value. So in that X direction, like we said before, the base is the direction it would be buckling. So my moment of inertia in that X direction would be 1/12 times 20 times 30 cubed. That gives me 45,000 millimeters to the fourth. And in the Y direction, we get 20,000 millimeters to the fourth. And then we just have to figure out which of your, well, I actually give you the XX direction as pin. So plugging this all in then, in the X direction, my critical buckling load, which we said was EI pi squared over KL squared. So plugging in my E is 200 times 10 to the third, I 45,000 pi squared, and then don't forget that K is 1 in this X direction. Also 2 meters, converting that to millimeters gives me 2,000. Multiplying all that through, I end up with a critical of 22.2 kilonewtons. So if you plug in those numbers, you end up with 22,200. Same idea with the Y direction. The only real difference is in the Y direction is now we have a lower moment of inertia, but we also have this this effective length factor of 0.5, or K is 0.5. Multiplying that through, I end up with 39.5 kilonewtons. So I have two different loads that would cause buckling, 22.2 or 39.5, and I have to say, well, what is the critical load? What load would actually cause the buckling? It's got to be the lower one, meaning we never reached 39.5 because it already buckled at 22.2. So you're going to pick the smaller of those two numbers, and this one will govern. All right, so that's what I have. And let me know if you have any questions and comments. As always, good luck, and I'll talk to y'all later. Thanks.